Hello scholars, today I am going to teach you about significant figures. So let's start with the idea, what are significant figures? So significant figures, let's unpack the term. There's significant, okay, so significant as you can imagine means important. And then figures is not actually referring to like shape or pictures or anything like that. It's talking about digits. So a digit, if you recall, if you have a number like 475, the number 475 has 3 digits, the 4, the 7, and the 5. So significant figures is talking about important digits. Why would I be talking about this in a science class? So there's some information. Basically, significant figures give us information about measurements that were recorded. It talks about how precise a measurement it was, or a measurement tool. And in general, more decimal places means more precision or more exactness, which is important when you're recording data and when you're reporting data. So to give you a straightforward example, if somebody asked me how tall I was, I could answer in a few ways. I could say I am 5 feet tall. So that is one way I could share my height. Now that is not my exact height, that's just my approximate height. So that can tell you that I may be estimating my height. Or I could say maybe that I am 5'2". I'm 5 feet 2 inches tall. So that adding that 2 increases the number of significant digits I have and tells you that that's a more exact measurement of my height. Or I could get even more exact and say I am 5 foot 1.75 inches. So that is even more exact. Now I have the 5 foot and I'm 1.75 inches. So that is even more significant digits or significant figures there. So that's an example. More significant figures you have, that tells you the more exact your measurements were. So let's look at some data. It's important for us to talk about how exact our measurements were. And so when we record our data in a data table and share that, we want to make sure that we are doing this appropriately. So here's 3 different ways that a scholar could present their data, and these are different ways I've seen data presented. Which of these ways would be the best? A, B, or C? One thing I want to clarify here is that the first 2 columns, mass of the metal and volume of the metal, those are measurements. And then this last one, density, that is actually a calculated value. So that's not a measurement, it's a calculation. Okay, so a lot of you might think that example A is the best way to present your data because look at all those decimal places, it must be so exact. However, that's actually not true. So we wouldn't want to use example A because our measurements only go out to 2 decimal places and 1 decimal place. So it's actually inaccurate to go out to 8 decimal places because we didn't measure to 8 decimal places. If we had measured both of these values to 8 decimal places, then you could report like that. But since we didn't, you shouldn't be reporting your data like that. So it is not example A. And then example C, there's a couple of issues here. One, we can see by looking at this that this is rounded data. They did not record all of the decimal places like they did in examples B and example A. The second thing is not only did they not go to the exact 0.0 on these bottom 2, but they're also inconsistent. Why would they record 1 decimal place for one measurement, but then no decimal places for the other 2 measurements? So you want to make sure to be consistent. So it is not C. So the best way to present your data is actually B. Let me give you some rules for how to keep that in mind. So the first one, you always want to record all decimal places for your measurements. We don't want to round our measurements. So that is why this example here is not good. We also want to always round our calculated values, okay, to the same number of significant figure as your least precise measurement. Least precise measurement. So that means your measurement basically with the least number of decimal places. Now, there is a little bit more nuance to that, which is it should be the same number of significant figures, which is sometimes not the same as the number of decimal places. But for our purposes, to make it easier, you want to just go with your smallest number of decimal places. So for example, here in our bottom example, we have 2 decimal places for the mass, but only 1 decimal place for the volume. So my final result will only have 1 decimal place. And that's how that works. Next, we want to look at some actual measurements themselves. Now, just looking at these 2 balances, which one would give you a more precise or exact measurement? So yeah, the analytical balance, which shows on it a measurement of 2.3199 grams, is more exact, more precise than the tabletop balance, which measures 301.7 grams. So that is because it goes out to more decimal places, obviously. And let's look at significant figures. So there are actually rules for determining if a digit is significant or not. In this case, the 2 is significant, 3, 1, the 9, and then the other 9 is significant, which gives us a total of 5 significant figures. And then over here in our other balance, the 3 is significant, the 0 is, the 1 is, and the 7 is significant. So that gives us 4 significant figures. So even though this balance only goes out to 1 decimal place, it still has almost the same number of significant figures as the big one, or the analytical balance. However, let's say, for example, if this, instead of being 2.3199, was 302.3199, now I have 7 significant figures, and that shows you how much more precise that balance is, the analytical balance, than the tabletop balance. Let's look at another example with pipettes. So from a glance, these are 2 different pipettes. We have a 1 milliliter pipette and a 10 milliliter pipette. Which one's going to give you more exact measurements? The 1 milliliter pipette will give you more exact measurements. So first, let's figure out what the measurement on this pipette is. From the picture, we can see that the pipette has been filled from the bottom up. So I'm going to measure from the bottom up. We always measure pipettes from the bottom of the meniscus, which is where that black line is. And if I look at this, it is 0.1, 0.2, and 0.25. So it is 0.25. Because it's exactly on that line, we're going to call this 0.250 milliliters. What about the 10 milliliter pipette? What is the measurement on that? This pipette works a little bit differently. So you'll notice that the 6 is actually on top and the 7 is below it, which means that this pipette has been drained, which means we actually start counting at the 6. So here we have 6.1, 2, 3, 4, 5, 6.6, but it's not exactly 6.6, it's a little past there. Now, if we look at the meniscus, it's not quite halfway. If I were to say, Yeah, that's about where the bottom of the meniscus is. So it's not quite halfway. It might be like 6.63 milliliters. So obviously the first pipette goes out more decimal places. However, just like in our other one, the significant figures may vary a little bit. Here we have in our 1 milliliter pipette, the 2 is significant, the 5 is significant, and the 0 at the end is significant. The 0 at the beginning is actually not significant. So this gives us a total of 3 significant figures. This other one here, 6.63, this also, each of those are significant, so this also has 3 sig figs. However, just like with our balance, if let's say that wasn't a 0, it was 2.250, then we would have 4 significant figures because the 2 would also be significant. These rules probably seem a little crazy to you right now, so let me break it down a little bit more. Why are some digits significant? Why are some not? Why are there some zeros? What does this have to do with precision? All of these are great questions. So here's some helpful rules for finding the number of sig figs in a measurement. You do not have to memorize them. You just have to be able to apply them if needed. If you plan on pursuing science, you will need to know sig fig rules, especially if that's something that you intend to study in college or make a career out of. They're very much sticklers about sig figs. So here's rule number 1. All non-zeros are significant. So that's pretty easy. There are 3 significant figures in 613 because they are all non-zeros. In 123,754, you got 1, 2, 3, 4, 5, 6 non-zero numbers, which means 6 significant figures. Number 2, zeros between non-zero digits are significant. So if I have the number 5,004, the 5 and the 4 by default are significant, and because there are zeros in between them, those are also significant. To give you an example of why, let's say this was a 0 on the end instead of a 4, and that's 5,000. In that case, I don't know if somebody just estimated. They're like, oh, it's about 5,000 feet away. Or we live about 5,000 miles from Europe. But it's not exact measurement. By putting that 4 on the end, that shows that that measurement is more exact. It's like, no, we live exactly 5,004 miles from Europe. 602, same thing. The 6 and the 2 are significant, and the 0 is also because it's between them. Third rule, trailing zeros, so zeros that trail or follow behind, are not significant unless there's a decimal place. So it's the same thing about the exactness of the estimate. So 1,200, only the 1 and 2 are significant. These 2 zeros aren't because we don't know if that's an exact measurement. However, if you have this decimal and it's 1,200.30, then they're all significant. And then you fall under that zeros in between rule, and then this 0 at the end tells you that you went that 1 exact. It's kind of like our pipette. We're looking back at our pipette here. We add that extra 0 because it's exactly on the line. So that tells us it's a more exact measurement. So that's what sig fig rule number 3 is about. And then lastly, our last rule, leading zeros. This rule has always confused me, but leading zeros, so zeros in front of numbers, are not significant. So again, back to our pipette, anything, if there's a 0 before the decimal place and there's a bunch of zeros before there's numbers, none of those zeros are significant. So in this one, only the 4, 5, 6 are significant. Same thing here. Even though there's a bajillion zeros and you're going out to, like, I don't know, the 10 billionths place, what is that even? Only the 4 and the 5 are significant digits. So that's sig figs in a nutshell. The most important thing to keep in mind, though, is how this impacts the reporting and recording of data. So the most important thing you need to remember is don't round your measurements. Record them exactly, estimate that last digit on a pipette or a ruler. But do always round your calculations. Please don't do this to me. When I read your like KERS or ERKs and I see 8 decimal places, I just like can't even, my eyes just glaze over. I have no idea what you're saying because the number is just so ridiculous. So don't do that. Make sure that you're recording all your decimal places and make sure that you are rounding your calculated values to your least number of decimal places. And that is all I